This presentation is on electron configurations, which merges together those orbital diagrams that we had learned about and quantum numbers. First thing we're going to do is label our periodic tables, or like color them or mark them up. Somehow we're going to split them up into these 4 different sections that are listed up here. So we're going to label the S block, which are these green elements. So the S block are the alkali metals, the alkaline earth metals, and all the way over here, helium would kind of like fit into this like little spot that is here. All right, so those elements are all part of the S block. Then we have our P block, which is the gold color, and those are all of the elements just to the right of the transition metals and all the way to those noble gases. The D block elements are all of the transition metals. And down here, the last elements in the rest of the F block. All right, so we have our 4 sections. Let's go ahead and mark up our tables. Again, it does not matter what color you use. So maybe I'll just do blue as the S block, put a little spot, S block elements. So again, those are the alkali metals, alkaline earth metals, as well as helium over here. Next we had our P block elements. Oh, I don't know why I'm changing that. All these guys over here are P block elements. All right, then all of these. And don't forget about those last 2 elements down here in the F block. Technically, they're D block elements. The way that you can tell is that if you look at the atomic number, this guy's 72, so the element right before it is 71. So that's part of the the D block, and then we have 104 here and 103 at the end there. Okay, so those guys are part of the D block. All right, last one to label are F block elements. So all of these letters might look familiar to you because they are the same shapes as we talked about when we were looking at quantum numbers. So there is a correlation between these, and we'll take a look at that a little bit later. But remember, in quantum number land, S represented a sphere or a circle, so the electrons were moving in that kind of shape. In the P orbitals, we had like a dumbbell shape. In the D orbitals, we had like an X or a clover shape. And then the F shapes were just like wild and crazy, and a whole bunch of orbitals kind of stuck on the center. So these 4 letters do represent those orbitals because the elements, the way that they're highlighted, the last electron of these elements would be in the corresponding block. All right, so for example, the last last electron of nickel would be in that D shape. The last electron in carbon would be in that P orbital shape, that like dumbbell shape. Okay, so it's marked up this way for a reason. The other thing I want to point out, on this first slide, we do have some numbers involved. So along the left-hand side of the table, notice how this just goes 1 through 7. So I'm going to go ahead and label that on my periodic table. All right, so period 1, 2, 3, 4, 5, 6, 7. Then, if you look at the D block, it downshifts in number. So for example, here it says 4s, but if I go to the D block, notice how it drops down to 3. The same thing happens here. 5 drops down to 4, and so on. So what I'm going to do is just write those numbers in here. So this changes to 3, this changes to 4, 5, and 6. Right, and technically, remember, there are 2 D block elements at the end of the F block, and they would fit in exactly where this 5 and 6 are. So that's what I'm going to label them over here. 5, 6. Now, if we go back up here, we'll see that after the after the D block is over, 4P, 4S. After D block's over, 5P, 5S. It goes back to normal. So I'm just going to make sure that I mark that on my table so I don't forget. So 4S, then 5, then 3D, then back to 4P, 5, 6, 7. And the F block is labeled 4 and 5. So 4 and 5. All right, so the only reason why the F block is down below the periodic table, if we take a look at the numbers, technically this guy would fit in just fine because we end at 56. Then it goes to 57, it counts all the way up to 71, and then it goes back to 72 in the D block. So this is just kind of like an insert of the periodic table, but the reason why it's separated was to fit in a textbook. So this is what that full-length table would look like. But it doesn't fit in books, so now it's split into 2. All right, so the different sections or blocks within the periodic table correspond to the S, P, D, and F sublevels. Again, those quantum numbers that we talked about. We can build the electron configurations of atoms by reading the periodic table in order of increasing atomic number. Electron configurations are like the address of the element in the periodic table. So the principal quantum number, n, is the row in the periodic table. So you might remember that the values that we listed for n were always going to be 1 through 7. All right, so notice how when we labeled our table, we never went up to a number past 7. This was the maximum whenever we labeled it. So that has to do with the fact that principal quantum number can only be 1 through 7. The shell of D being filled across each new row is equal to n minus 1. So remember how I said that the D block kind of switched its numbering? This is what they mean by that. So like if S was 4S, remember, then it went to 3D. It was n, which is 4, minus 1, it became 3. All right, so that's that downshift in the D block. Okay, so again, 4S, then it goes to 3D, and then it goes back to normal, 4P. The shell of F being filled across each row is equal to n minus 2. So you don't necessarily need to know that like D is n minus 1 and F is n minus 2. Just know that when you're labeling your periodic table for like a test or a quiz, yes, you get a blank one, but you can fill it out. You need to know that like F block here is 4 and 5. And then that D block downshifts. Sorry, I keep scrolling back and forth, but it's easier to show you that picture. All right, so the maximum number of electrons. There are 2 columns in the S block. One s orbital can hold a maximum of 2 electrons. Remember, there is only one s orbital. So when we were filling out those energy diagrams, there was only one line for s. Maximum of 2 electrons. Remember, one orbital can hold 2 electrons, but they have to have opposite spins. I don't know why I did that. The next one says that there are 6 columns in the p block. The 3 p orbitals can hold a maximum of 6 electrons. If I take a look at the p block of the table, right, again, there's 6 elements going across. 1, 2, 3, 4, 5, 6, which means that I need to be able to account for 6 electrons. When you guys were looking at the orbital diagrams and filling in how many electrons fit in those, there were 3 p orbitals. So like p, 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 remember they're the same energy level. So this could be like 2p, for example. Right, and 6 electrons, 1 in each orbital first. Remember, electrons don't want to have anything to do with each other. They're going to occupy separate orbitals. And then once they run out of room, they're like, okay, well, I guess I'll have to pair up, but in the opposite direction. They spin in the opposite direction. So we have 6 electrons. The same is true for the D block. If you count the D block across, which I'm not going to keep scrolling up and forth, like back and forth, because I feel like it might give you guys a headache. It's 10 elements across. That tells us that it can hold 10 electrons. If an orbital can hold 2 electrons, that means that we have to have 5 orbitals there. And when you guys filled out your orbital diagrams, there were 5 orbitals for D. Again, 1 electron in each of those orbitals first. Then when they run out of room, they pair up with a spin in the opposite direction. I just drew a total of 10 electrons. Same is true for the F block. If you were to count that across, there's 14 elements. That's the way to remind you, or that's a way to remind you that there's 14 electrons. If an orbital can hold 2 electrons, that means that there are 7 orbitals there. All right, so that could be like 4F. Remember, it's 4F or 5F. Those are the only 2 options for F. And I could fill in my electrons, filling order. Remember, 1 in each orbital first. 1, 2, 3, 4, 5, 6, 7. And then the opposite direction. 8, 9, 10, 11, 12, 13, 14. All right, so number of the elements across is the same as the number of electrons. Just have it to figure out how many orbitals there are, because each orbital can hold 2 electrons. So we're going to do some examples. We're going to write the complete electron configurations for the following elements. All right, so the first one is fluorine. First thing you want to do is find where fluorine is on the periodic table, and it's number 9. So that tells us some information. We should have 9 total protons, which equals 9 electrons. Again, we're writing the electron configuration, so that's really what we're concerned with. We're going to go across our table. You always start with hydrogen. That's always going to be the first element that you start with. It's going to be like reading a book. We're going to write down what the principal quantum number is. 1, 2, 3, 4, 5, 6, 7. And remember the D block goes 3, 4, 5, 6. Here's the 5 and the 6 for those guys. And then it goes back to normal at the end of the D block. 4, 5, 6, 7. This also corresponds with, remember those blocks that we had colored previously. So I'm not going to color it because it's going to take too much time, but this was S. Remember, this whole middle section is D. This section over here is P. Don't forget helium is technically a part of S. And then we have our F block down here. And this is 4 and 5F. So we're going to go in order until we get to fluorine. So here's hydrogen. It's in principal quantum 1. The block that it's in is S. And technically, remember, helium's like it's over here. I'm going to have to go through hydrogen and helium in order to get to fluorine, right? Atomic numbers are 1 and 2, and fluorine's number 9. So this little superscript tells us how many elements we have to pass through, or how many electrons are in those orbitals. All right, so we got to 1s2. Now, if we're reading from left to right, the next place we're going to go is lithium, which is right here. Well, that's period 2. We're still in block S there. And I have to go past both lithium and beryllium to get to fluorine. That's 2 elements that I have to pass through. If I keep going past beryllium, my next element is boron. But now we're in a different block. So anytime we start a new row or we start a new block, we need to relabel that. So I'm still in period 2, but now I'm in block P. And I'm just going to count, since I know that fluorine is in this row, which element number chlorine, or like which element in the block fluorine is. So here's 1, 2, 3, 4, 5. All right, so the electron configuration for fluorine is 1s2, 2s2, 2p5. Okay, if I add up these little numbers, 2 plus 2 plus 5, I should get the the number of electrons that fluorine has, which is 9. That's how you know you did it right. All right, so this is the electron configuration for fluorine. What this is telling me goes along with those quantum numbers, that in that first kind of energy level, there are 2 electrons moving in a sphere shape. I'm going to do my best to draw a 3D picture, which is not going to be very good. But here's like my axes. Here's like the weird z-axis. All right, so I have 2 electrons. And remember, principal quantum number 1 means those electrons are moving kind of close. So somewhere in this like yellow area I'm about to shade, S is a sphere shape, there are 2 electrons there. And I know that because of that little 2. Then I also know, well, there's 2 more electrons moving in a sphere shape, but their principal quantum number is 2, which means that it's a little further away from the nucleus. So like somewhere in this area, there's going to be 2 more electrons in addition to those initial ones. All right, well, let's move on to the P's. We have the same principal quantum number, which means same distance from our nucleus, but now we have p orbitals, and I have 5 electrons in those p orbitals. So I'm actually going to switch this to the green pencil because I'm going to stay the same distance away. I'm going to have, here's one of the p orbitals, here's another one of the p orbitals. Notice how I'm drawing them the same distance away as like 2s. Again, principal quantum number means distance away from the nucleus. And then I'll have like that 3D one on the x-axis, or sorry, the z-axis. And I have 5 electrons in those orbitals. Let's move on to the next one. So electron configuration for magnesium. All right, so the first thing I'm going to do is maybe label this table again. 1, 2, 3, 4, 5. I could keep going, except I know magnesium's right here, so I'm really not going to keep going. You can if you want, but our atomic number is only 12, which means that I'm only going to have 12 electrons. I'm not going to need those like super large principal quantum numbers. All right, and then blocks S, D, P, and then don't forget helium's technically over here, so I can just kind of draw it in. All right, well, we're going to get to magnesium. So magnesium has 12 electrons because its atomic number is 12. So again, start with hydrogen. Hydrogen is in row 1, it's in block S, and I have to pass through both hydrogen and helium to get to magnesium. So that's 2 elements. Brings me to my next row. I'm in period 2. I'm still in block S, and I have to go past lithium and beryllium to get to magnesium. That's 2 elements. All right, if I trace across the table, again, like reading a book, I'm in row 2, block P, and I have to pass through all of these elements to get to magnesium. 1, 2, 3, 4, 5, 6. All right, brings me to my next row, which is sodium. All right, sodium is in period 3 in block S, and magnesium is right there. So 1, 2. All right, so I'm going to go ahead and add up my superscripted numbers and make sure I get 12. So 2 plus 2 is 4, plus 6 is 10, 11, 12. Perfect, that's 12 electrons. All right, last one, I think, yes, is the configuration for nickel. If I take a look at nickel, it's right here in the table. So I'm just going to go ahead and label things up to there. So 1, 2, 3, 4. I'll go 5, even though I don't need that. Remember, in the D block, there's a downshift. So this is 3, 4. And then after it, this would go back up to 4, 5. All right, S block, D block, P block. And then this is technically helium again, is technically S. All right, so to get to nickel, there's 28 electrons. So our configuration would be 1s2, 2s2, 2p6. That brings me here. Next row is 3s. I have to go past both magnesium and sodium, and I keep going across the table. I'm in row 3, block P, and I have to pass through all of these elements. That's 6 of them. All right, next element here is potassium, which is in period 4, block S, and I have to pass potassium and calcium to get to nickel. Remember that downshift in number. I'm in row 3 now, because there's a shift down, in block D, and I'm going to count how many elements in nickel is. So here's D1, D2, D3, D4, 5, 6, 7, 8, D8. All right, and if I add these little numbers up, I should end up with 28. All right, so here we have 4 plus 6, that's 10, plus 2 is 12, plus 6, 18, plus 2 more, 20, plus 8, 28. Perfect. All right, we wanted 28 electrons. There is a way to simplify the electron configuration by using valence electrons. Remember, we talked about this in physical science a little bit. Valence electrons are the electrons in the outermost occupied shell of an atom. So basically, we're looking at the highest principal quantum number. All right, so the core electrons are the ones that are in the filled inner shells of an atom or ion. These guys are not involved in chemical reactions, so we don't really need to list these every single time. We can simplify our electron configurations by writing the most recent noble gas closest to atomic number without going over in brackets and pick up from there. All right, so the bracket part are going to be those core electrons, which again, we're not that interested in. They're sheltered, they're not going to participate in chemical reactions. So we can just kind of list them as like a group, and then after, we'll list those valence electrons. And again, these are going to be the ones with the highest principal quantum number. If we take a look at this, okay, we're going to write the complete electron configurations for the following elements. These are the same ones that we just did. So I'm actually going to copy the electron configuration. Well, this one's like a mess, so I'm going to rewrite it. All right, so fluorine's electron configuration was 1s2, 2s2, 2p5. Magnesium, and this, I'm just getting this from the previous slides, writing out the configuration. 1s2, 2s2, 2p6, 3s2. And then nickel, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and it was 8. All right, so those are like the full ones. Now what we can do is use the noble gas configuration to make them shorter. I'm going to take a look at fluorine. I'm just going to use this slide temporarily. Fluorine's here. The noble gas before it is helium. So my shortcut will be helium in brackets, and then I'll continue from there to fluorine. So 2s2, 2p5, 2s2, 2p5. Notice how these numbers are the ones, the highest principal quantum number, right? We eliminated 1 because that was the lowest principal quantum number present. So we can do the same thing for magnesium. So if I take a look at magnesium, and I'll clear this slide. If I take a look at where it is, right here, the noble gas before it is neon. Remember, this whole row is noble gases. So the noble gas before it is neon, and then I'll continue from there. So neon, and then 3s2. So neon in brackets, and then 3s2. Again, notice how we eliminated the lowest quantum numbers, and we're only left with the highest principal quantum number. Okay, we can do the same thing for nickel. Oopsie. So we can do the same thing for nickel. All right, nickel is right here. So the noble gas before it is argon. So we're going to put that guy in brackets, AR, bracket, and then continue from there. 4s2, 3d8. All right, so in this case, we eliminated everything up to 4s2. So all of these are combined by using argon. And then 4s2, that's the highest principal quantum number. And then remember, there's a downshift, but we still have to include the 3d8. You guys can also check your answer for these by looking at the number, like the atomic number of the noble gas. So like if you take a look at fluorine, we know that we should have 9 electrons. Well, helium consists of 2 because its atomic number is 2, plus these 2 electrons plus 5, which gives you 9. All right, same thing for magnesium. If you look at neon on the periodic table, that's number 10. So 10 electrons plus 2 more equals 12. That's perfect, okay, because magnesium is number 12. Same thing with nickel. Argon is element number 18, plus 2 plus 8. That gives me 28, which is the number of electrons that nickel has. All right, so a lot of times we'll use this noble gas configuration to shorten our configurations for elements that are a little lower on the table. So for this one, it wants us to write the electron configuration for a tellurium, which is this guy over here. All right, so really quick, I'm just going to go ahead and label 1, 2, 3, 4, 5, 6, 7. This goes 3, 4, 5, 6. And then back up 4, 5, 6, 7. All right, and then I already know the blocks, so I'm not going to label those. So tellurium's over here, noble gas before it, krypton. So I'm going to go ahead and put Kr in brackets and then move on to the next element. So krypton's 36, Then I pick up with rubidium. Period 5, block S, I have to pass both of those elements to get to tellurium. All right, then now there's a downshift in the D block to 4D, and I know that it's 10 elements across, and I know I'm going to have to pass all of those to get to tellurium. Back up to 5, so 5, ugly, sorry, 5P, and then tellurium is 1, 2, 3, 4. Again, let's just really quickly check our count for electrons. Krypton's 36, plus 2, plus 10, plus 4, oops, not 14, plus 4. All right, that's going to give us, what, 8, 36, 37, 38, 48, plus 4 more, 52. Perfect, because tellurium's number 52 on the table. So we're accounting for all 52 electrons. All right, next one, our configuration for bismuth. Bismuth, this guy right here. All right, so that looks pretty low down on the table. Looks like it's even past this like weird switch in elements right here. So let's go ahead and label everything. So period numbers, 3, 4, 5, 6, 7. Downshift, 3, 4, 5, 6. But technically, remember, 5 and 6 start down here. Then we'll go back to normal after the D block with 4, 5, 6, 7. And then F block is 4 and 5. All right, so if we're going all the way down to bismuth, noble gas before bismuth, xenon, Xe in brackets, and then we keep going. 6s2, and then looks like our next element after 56 is 57. So we're going to list 4f. We go through all of these because bismuth's number is 83. So we go past 70 for sure. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 elements across. So I need to put 14 electrons there. And then the next spot is 5D. All right, and remember, after this is the block is over, it kind of fits in right here. So this is 5D1. Here's 5D2, 3, 4, 5, 6, 7, 8, 9, 10. 5D10. Shifts back up to 6P, 1, 2, 3. All right, so we want the total to add up to 83. We can double check. 54 for xenon, plus 2, plus 14, plus 10, plus 3, 83. Okay. So the next questions or next slide just have us figure out what element configuration is given. So first one, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Usually, if you're trying to find an element, you could just go to the last one. So if we're looking at 3d, they're talking about this row here. So we're looking for the 7th, yes, element in 1, 2, 3, 4, 5, 6, 7. We are talking about cobalt. Next one then, looks like we're starting with argon, so they're using the noble gas method. 4s2, 3d10, 4p5. Again, usually we could just look at that last part of it and figure out which element it is. So period 4, block P, 5 elements in. Here's 2, 3, here's 4. And then, what was it, 5th element? Yeah. 1, 2, 3, 4, 5, bromine. that is it. Hopefully that helped you understand quantum numbers a little bit better.